What is a VOC? So it's a volatile organic compound. It comes in many various guises. Two important things about volatile organic compounds is they evaporate at room temperature. So what we're talking about here is something in its gaseous state. You can get very heavy organics, which you can't detect with the technology we're talking about. When we talk about organics, essentially we're talking about anything with carbon in. So this is a very large, very multifaceted group of chemicals, and as you'll see in the presentation, it covers many areas of both industry and usual domestic exposure and air quality. Sometimes there's an extra delineation between them. So you have your very volatile organics, which are your lighter ones, and your semi-volatiles, which are your larger organics, so less likely to kind of be around in your monitoring atmospheres. So general typical VOCs. So let's go through the list here. These are compounds you'd see in a variety of applications. So acetone you'll see commonly used as a solvent. Benzene used to be used as a solvent. We're trying to clear that out now. Also used as a feedstock for general chemical processes, naturally occurring fuel as well. Get your formaldehyde, which is used for preservation and storage of things. Perchloroethylene, which is a very good solvent and is used in the dry cleaning industry. So you can see on the right-hand side here is a splash of different VOCs. The things which they bear in common is this carbon center to them. So the black molecules or the black atoms here represent carbon. So anything with a carbon chain is delineated as a VOC. Just for a bit of historical interest, I was dialing around. So our humanity's general love affair with VOCs, where does it start? So we go back to ancient civilization. We actually managed to ferment this vegetable matter to create ethanol. This is good for dissolving our oils. Also the ancient Syrians sealed up wood and heated it for methanol. And the Egyptians as well. There's been some studies showing that the actual cosmetics which the Egyptians used were based on synthetically manufactured solvents. So for many thousands of years ago, we have been using these chemicals. Say in the 9th century, there's a first literary evidence of solvents and organics used for medicinal purposes. But it's in the 1900s where we really see the explosion of the use of solvents. You see the widespread industrialization and the use of coal turning to the use of oil. The majority of the solvents we use are byproducts of oil, and the industrial processes we've got, say manufacturing of plastics, use of solvents in industry, has really exploded over the course of the 20th century. So part of the evidence and the information I'll present here is how we're trying to keep up with this explosion, this use of the VOCs, what we found out about them, the dangers of them, and how we can help to control them. So first off, why do we want to monitor VOCs? There's four main reasons. First one is effects on human health, effects on the environment, to uphold regulatory standards, and also for financial benefits. So these are the four main reasons, and I'll go through these one by one and highlight how VOC monitoring can benefit this and the needs to monitor VOCs in these regions. We can monitor VOCs for financial benefits in terms of reducing our consumption of chemicals, and also opportunities to reduce solvent costs. So what we're doing, what we plan to do with this kind of monitoring is inline feedstock monitoring, checking on the quantities of VOCs or solvents we're using, monitor them, and assess what are the best practices to regulate the monitors regulate the VOC use in our industrial processes. So this is much more to do with how we can control VOCs and using the monitors as a just to cover our emissions, cover our usage, and account for our VOC usage through that. There's also the regulatory standards. So there's a number of regulatory bodies around the world setting a number of different standards. And there's also some general points upon which we want to uphold these standards. So one general standard would be to meet emission limits. So we're talking about boundary monitoring or exhausts from industrial processes, and using VOC monitoring to account for that and ensure that we uphold whatever regulations are imposed on that particular process or industry. VOC monitors can also be used to commission techniques. So if you have a solvent abatement plant in an industrial process, you can actually use VOC monitoring to commission whether the techniques which are employed within processes are efficient and effective. And also there's health and safety regulatory standards. So to confirm with personal exposure limits for the harmful and toxic substances which might be around, is a natural byproduct of industrial processes which we can't necessarily monitor or control, but we need to monitor to ensure that we don't expose workers to dangerous levels. The other reason for monitoring VOCs is risk of health to workers and health to the environment. And this is further split into more levels. So with each VOC there's a defined explosive limit. There's the lower explosive limit and the upper explosive limit. So if there are particular VOCs within the environment which are deemed explosive, which is dependent upon what chemical they are, then you'll need to monitor whether the ambient levels are within these explosive limits. There's also toxic exposure. So this is continuing the theme of exposure to the workers, ensuring that people are safe and healthy. VOCs are also responsible for ozone formation. I was quite surprised when I was doing research for this presentation that there is a strong concern in terms of the reaction of VOCs with NOx's, nitrous oxide, to form ozone or smog within urban environments. And there's also VOCs also responsible for ozone depletion. So if we break this down a bit further, so in terms of toxic exposure, there's thousands of VOCs which are met in the different industrial processes. Say one of the big ones is refinery oil processes, also use of solvents in industrial processes and solvent manufacture. And each chemical has its own toxicity risk. You'll find there's two bodies, NIOSH and OSHA, which are regularly quoted here. And for each particular chemical, there's a STEL rating and a TWA. So STEL stands for short-term exposure limit. So with this, you average the exposure over 15-minute periods, and TWA is time-weighted average. So you're averaging your exposure over 8-hour periods. So your TWA is based upon what a worker would be exposed to over a normal shift. The STEL is usually used for more toxic, more dangerous chemicals. So you're wanting this short defined time, this 15-minute time, to ensure that exposure isn't lengthened over hours exposure. Because of the complexities and the number of VOCs there are less is known about the combinatorial exposure. We have within industries there's an unlimited mix of VOCs. So we understand the exposure for many chemicals, particularly the most hazardous ones, in terms of their individual capacities for harm. But because of the complexities of gas mixing and the industrial processes, less is known about this. So there's still a lot of work going on at the moment to define the dangers and hazards of VOCs. So with the Stellentois, you have your short-term risks and your long-term risks. So your short-term risks occur over hours and days, and your long-term risks are years or lifetime, and they come with them their own particular risks. So with the acute one, so if you're talking about a daily exposure or kind of an hourly exposure, then you'll see uncomfortable, unpleasant, and sometimes quite hazardous illnesses, sometimes headaches, vomiting, dizziness. Usually nothing particularly dangerous, but something unwanted. When it comes to chronic exposure, and this is something which we're still learning about and we're still researching, then you can get fatal diseases and illnesses. So we already know for particular chemicals, which I'll discuss later, that they are directly known to cause cancer, liver damage, kidney damage. So when we're talking about exposure to VOCs in a particular application, it's very important to know what VOCs you're going to be exposed to and the particular dangers. Some of them can be very benign, but some of them can be very dangerous in very small quantities. So if we briefly talk about ozone formation, there's a lot of material in this talk, and some bits I might just skip over. So with ozone formation, you're talking about the combination of VOCs and nitrous oxide. Usually this is we find this a lot in urban environments. So you'll see the combination of those two with the UV exposure, the bright sunshine. So if you have a particular urban situation, we have bright sunshine, heavy traffic, very low winds, and lots of traffic around, then you'll see a general increase in the amount of ozone. Ozone itself, being a byproduct of the abundance of VOCs, is dangerous to human health. So one limit given this is 50 ppb over an 8-hour exposure period. And this gives you respiratory damage, also headaches, nausea. So it's something used in quite a lot here for city-based monitoring. Down in London, so I come from Cambridge, and in London there is currently a widespread program where thousands of small monitors have been installed around London, and we're doing a long-term investigation into the relationship between VOCs, NOx emissions, and the ambient ozone. We know that there is a definite correlation between these, but the actual correlation between them is very complicated. I'll skip through this because it takes a while to go through, but effectively what you see is your VOCs create with your OH radicals some other radicals. These combine with nitrous oxide to form NO2. The NO2 combines with the light to form an O radical, and that connects with the oxygen to make ozone. As you can see on the right here, this is what's called an isopleth plot. So on the vertical scale is your NOx, on your bottom scale is your VOC, and you have this wonderfully complicated graph of potential O3 emissions here. So there's a number of things which are based upon the O3 generation, downwind distance, particular VOCs used. So this is an ongoing work in order to clean up urban environments. Just briefly to give you some idea of the levels we're looking at here. So these are levels of ozone. So before the 20th century, pre-industrial, in the environment we saw 10 to 20 ppb. Nowadays, in remote locations, we see 20 to 40. So even areas away from urban areas. In rural areas, when there's what we call particular pollution events, then this can raise up to 80 to 100 ppb. In urban areas, this rises even further to 120 to 200. So what you'll see with the urban areas being the epicenter, but there's a large drift with wind of the O3, of the ozone, into rural areas, which can also harm agriculture and forestry as well. In terms of recorded ozone levels, if you're unlucky enough to live in LA or Mexico City, where it's nice and hot and the air's full of smog, you're actually seeing levels around 490 ppb. So if we compare this to the EPA health standard, the standard at the moment is 125 ppb, which they want to revise to 85 ppb over an 8-hour period. So what you can see is a lot of work still needs to be done in terms of ensuring that the ozone generation, the VOC emissions from traffic and air cleaning is brought down to clean the air in our environments. And there are a number of cities around the world where this is known, and there's a lot of work going into this. Very briefly, also we have the ozone depleting substances. So your things here is CFCs. So CFCs, chlorofluorocarbon. They have carbons in, therefore it's a VOC. So this is just a trend. So one of a number of graphs I'll be presenting showing you the trends upon regulations coming in. So what you can see here, 1987 is the important year. This is the year of the Montreal Protocol. So there was this is where the kind of worldwide global registration or regulation came in for the restriction and end of use of CFCs. So it was found that the CFCs were destroying the ozone layer, responsible for global warming and other environmental hazards. So as you can see, we're happy using it up until the mid-80s, and by 10 years later, with compliance and changes in standards and use in CFCs, we managed to clear these out. So in terms of where we're exposed to VOCs, this is for the UK, but it shows a general trend of where we'll see this. The biggest use of VOCs is with solvents. There's also a very large exposure to VOCs within extraction and distribution of fossil fuels. So within the oil industry, well, oil is a veritable cocktail of VOCs. Effectively, that's what it is. So there's no wonder that we'll have a large exposure to that as well. And the big blue segment is for transport. So here we're talking about burning of fuel, so access to fuel vapors and also exhaust fumes as well. So these three, the solvents, the transport and the fossil fuel, are really the main industrial sectors where both emissions for environmental impacts need to be monitored for. Also a lot of human exposure to VOCs and health hazards we need to monitor for. Briefly, there's a small red wedge there for domestic exposure, and I'd like just to kind of provide where we are with VOCs and domestic exposure. A big thing which has come up recently, and certainly something we've found in Iron Science, is a need for indoor air quality. With new building designs, we find that we make these enclosed buildings with this recirculating air conditioning, which means we don't have a free ventilation into the atmosphere. And the problem is a number of our products contain these VOCs, and we're finding now with modern building design that there's real dangers to human health, even in terms of just everyday well-being, in terms of exposures to VOCs. As you can see, pretty much every aspect of our daily lives will have VOCs there wafting off. if you buy new furniture, that will be filled with VOCs. Commissioning for new offices, paint drying off, even say new cars, the new car smell. Sometimes they spray cars with their own new car smell to make it smell nice. And effectively that is just a whole bundle of VOCs waiting to be inhaled. So I present just a very quick, interesting slide which further demonstrates how our use of VOCs has changed throughout the years. So this is based upon PCE, which is perchloroethylene. So perchloroethylene is both defined as a human carcinogen. So it's I think it's a class 2B. So there's strong suspicion or strong evidence that this can cause terminal illness with extended exposure. It's also a well-known ozone depletion, so a CFC. So, as always, back in the early 19th century, Michael Faraday, we come up with this lovely chemical, unbeknownst to us, the dangers which it presents to us. In 1840, we see the start of the dry cleaning industry. Dry cleaning industry is very focused on the use of solvents. And I say solvents are a common theme you'll find within the exposure to VOCs. In the late 19th century, we're using spirits, oil, benzene, naphtha, used as dry cleaning solvents. So in this period of time, we're really quite gung-ho about the various chemicals we use. Come the early 20th century, raw white gasoline is used as a cleaning agent, which is quite scary. This is actually something which was realized by the insurance companies. The true fact is that the insurance companies decided to refuse insurance policies to dry cleaners because they kept on catching fire and exploding. This wasn't good for the dry cleaning industry, so along comes PCE, very effective, very useful cleaning agent. So these bars now, so mid 20th century, these bars are representing the general PCE use. So by 1948, we've cleared through the use of the gasoline and the more immediately dangerous chemicals, and PCE becomes the real leader of the dry cleaning industry. By the 60s, PCE accounts for 90% of PCE consumption. But then with the onset of illness, regulations, laboratory work, the evidence starts to rack up about the dangers of PCE. So in '85, the EPA published an intent to list the PCE as potentially toxic. So there's the first warning signs that something's not right here, something is very unhealthy. Come 1987, as I showed before, there's the Montreal Protocol, which is another hit on PCE. Following that, there's lawsuits against dry cleaning facilities. The PCE is found in groundwater samples. Following from that, the phase out of Freon 113. So this is another CFC, very similar to PCE. Come 2000, there's now regulation for all dry cleaners in the south coast of America to phase out the use of PCE. And then the EPA has declared by 2020 that all existing PCSE and dry cleaning machines are to be prohibited. So this is it's a standard procedure we're seeing here. Come the mid 20th century, late 20th century, there's been a real boom in realizing the dangers of VOCs, regulation of VOCs, and the need of industry to bring these regulations into reality and find alternatives for these. So in terms of monitoring methods, what general monitoring methods are there for VOCs? So we're talking about industrial applications here. So there's three main types. There's a grab sampling. So what you're doing here is just taking a single sample over a period of time and taking it back for analysis. So this is for long-term trending analysis. You also have portable analyzers. So these will be devices which you take on site, so you can do real-time screening there. You don't do long-term monitoring in a sense, but you can go to a site, search around, and in that short period of time, you can see if there's any local emissions which you need to be aware of, which you need to control. And there's also continuous monitoring. So aside from these two, you can also install a fixed monitor. So this is this will continuously monitor your VOC emissions. So it will give you a long-term feedback of the trending of VOCs. Sometimes you can have a data control center, so you can link your VOC exposure with particular processes going on in industry. You can also use them as local alarms, so you can attach beacons to them, or generally ensure that the workers, if there's no particular vicinities where VOC problems are, you can ensure that those places are continuously monitored, so you don't need to instigate new monitoring procedures. You just have that one fixed monitor, and that does the work continuously for you. So if we talk generally about personal monitors, so personal monitors are ones which the worker would wear on themselves. So these are designed to protect the health of the worker. You're less concerned about the control of processes or leakages. What you're concerned with is how much of a VOC exposure there are to the worker. And there's 4 different kinds here as well: a passive and active sampler, instrumentation, which is worn, and instrumentation in the hand. So with the passive sampler, you either have these badges, as you can see on the slide. So what these will do is it's usually just an absorbent. It won't give you any immediate feedback to the VOC levels exposed to. So it will passively absorb the VOCs and the local atmosphere around the worker, usually worn for a day or so to ensure that you get a long exposure time. And then those badges will be taken back to the analysis for offline analysis. These are very cheap, so what you can do is give them out to many workers, collect them all at the end of the day, and do a large batch testing in the laboratories. Obviously with these there's no immediate feedback, so with this you get a general indication of the exposures which the workers are exposed to. You won't get any immediate feedback from that. Also being very cheap, they're very dependent upon the atmosphere you're around, so dependent on the wind speeds and the ambient temperature, depends on how efficient they are for collecting up. So it's basically a very simple, cheap control method, but it's very good for wide scale, large quantities of monitoring for a large number of people. There's also direct reading devices. So rather than the samplers which are taken away to be monitored in a laboratory, these ones have a visual indication. So these will actually give the local worker an immediate indication as to the VOCs which they're exposed to. But with this, they are cheap, but at the same time they're very limited in their capacity. Usually it will just be a total VOC reading, and it's very much dependent upon the environment. So it's a very, very rough reading of what the worker is being exposed to. You do get a slightly more advanced one, your active sampler, and generally what this is a passive sampler with some airflow attached to it. So one of the problems with the passive sampler is its uncontrolled access of the environment to the absorbent layer, absorbent coating material. So with an active sampler, for a small extra cost, you can actually more closely define and more closely control the access of the ambient sampling environment to your monitor, and this is usually used with a tube. So you see a very, very simple setup, and just gives you that little extra bit of accuracy in your measurements. You have your battery charging and your other upkeep for these, so not quite as simple, but it's a balance to make. Then you come on to your personal instrumentation. So as you can see here, this is actually a PID instrument which we make attached to our work here. This is the cub. So what this is a personal PID monitor, which I'll talk about in a minute. So this provides a immediate response to VOCs, gives you a continuous readout. So it comes with a safety alarm, and what it will do is it reads the given ambient concentration of VOCs at any given moment. So so it's a real time. So as the VOCs go up and down, so does the reading on this monitor. And with these monitors, you can have safety alarms on them. So you can, so the worker can be immediately alerted to when they're in hazardous environments. Plus, you can also have data logging on this, so you can take these back, and the central control system can monitor and review how much of an exposure various people have had. You can also link, where you can link up these monitors to different data sets and where people have been. So you can also use this as a general multi-monitor around industrial processes. On top of the personal monitor, we have the handheld instrumentation. So that the personal monitor chronologically has come after the handheld instrumentation, and mainly it's come about by the miniaturization of technology. So in terms of our instrumentation, it has started off with our handheld devices, and still with handheld devices are the benefits. There are extra benefits which you usually won't see in the portable devices, although they're slowly coming into effect. With your handheld devices, you have your sample flow there. You can also have the additional accessories, so you can do selective measurement. It has these safety alarms, but there'll be additional safety alarms configuration you can get through it. And generally, it's a much more configurable, much more usable piece of equipment. You can have long probes, so you can measure VOCs down in reservoirs or down in places where you might not want to go with a personal monitor. Yep. And also you have your fixed monitors. So with these give a immediate response to VOCs, and effectively these are mainly used as safety alarms. As you can see here, there's two here: our Corvus and our TVOC. So the TVOC is a PID monitor used in intrinsically safe environments. So effectively, what this allows is a long-term service-free instrument which you can plug onto the wall, install into your local quality systems, safety systems. So not only will that give immediate feedback to the users at hand, but usually you'll have some kind of output as well, 40 to 20 milliamps or RS485 Modbus. So you can communicate, log in, connect these monitors to your local safety system, so they can raise up alarms around your plants, which can then bring in effect shutdowns to processes or other health and safety measures. The final monitor is, say, selective monitors. So the technologies we've talked about so far, the particular monitors we've talked about so far, are general VOC monitors. I'm making a slight discrepancy between the selective monitors and the fixed monitors. But as time goes on, we'll see a lot with the handheld monitors and the personal monitors where the technology starts to, there's less of a definition between them. You also find that with the selective monitors here, which are usually very expensive and require highly trained technicians, we are starting to see this kind of performance and this kind of functionality come into our wall-mounted monitors. With selective monitors, the real benefit is the surety of what you're measuring. As said, VOCs are a very wide, very diverse group of carbon-based compounds, but also they share a lot of similarities. So chemically, it can be very hard to discern between one chemical and another, and currently it requires some quite clever analytical techniques to be able to discern exactly what VOCs you are particularly interested in the environment. You'll usually find when you're monitoring for VOCs in environments, it will be a cocktail of things. Very rarely do you find one particular VOC which you want to measure. So this can be very helpful. So if I briefly go over the four main technologies which are used in VOC monitors at the moment. So the PID is our main technology. Unfortunately, I haven't got a picture of how the PID works. I was looking around for a good picture, but unfortunately, you just got a picture of our PIDs here. So I hope you don't mind. But effectively, the way it works is the area is ionized by a UV lamp, and depending on the amount of VOCs within the environment, the generation of the ions from this UV lamp will be proportional to the concentration of the VOC. So what we get with PID is a very fast response, usually within a couple of seconds, to local levels, and non-destructive. There's no consumables with this. You'll find in terms of lifetime of the PID is dependent upon the lamp. Lamp could usually last from 6 months to 1 year, and there's some degree of servicing involved. Depending on the atmosphere, your window of the lamp might get quite dirty, so you might have somebody have to come and clean it up and do a test of those. But generally, over the life period of the lamp, they're very reliable. They're also very wide range, so you can go down to single ppb digits now, and up into the thousands, tens of thousands of ppm of VOCs. So they're very, very useful for a wide range of VOC applications, and we use them in both our personal instrumentation, our handheld monitors, and also fixed monitors as well. So they cover the whole range of bases. One of the limitations of the PID is that it's not specific. So any VOC which comes into contact with the PID will be detected, apart from very small VOCs such as methane, ethane, propane, and also different gases give different responses with the PID. So when using a PID, you need to be very careful, or you need to understand what particular VOCs you'll be monitoring, so you can effectively use a calibration factor with a mini PID. So when you look at the response of the mini PID, you know what concentration it is, because you know what gases are going to be exposed to. Along with the PID, there's the FID. Been around for about the same time. So the flame ionization works on the same principle as an FID, but with this you're actually burning a flame inside. So you're passing hydrogen gas through with your sample and burning that sample, and from that flame you generate ions, and as with PID, the proportion of the amount of ions generated from your sample is proportional to the number of VOCs in your sample. Flame ionization is very reliable as a detection method for many reasons. One thing is its true carbon count. So it actually gives a very reliable, dependable response dependent upon the VOC. So you see with VOCs, they have different amounts of carbon in them. So what you'll see with a flame ionization detector is that its response is proportional to the number of carbons. So if one compound has twice as many carbons in it than another compound, then you'll get twice the response. So you don't need to deal with response factors. And it's also very linear, so no matter how much gas or VOCs are around, it always gives a response dependent or very directly proportional to the number of VOCs. There are a number of significant deficits to the FID technology, though. One thing is the fuel consumption. One thing you'll find with VOC monitoring is a lot of it, especially with the solvents or oil industry, is that you'll be monitoring a lot in hazardous environments, I mean, especially explosive environments. And as you might understand, it's very hard to certify an instrument to be used in a explosive environment if in the center of it it's actually got a hydrogen flame burning. So it's very hard to use this in explosive environments. It's also destructive, so you're burning the sample. So if you want to, there's no chance of once passing through the FID, you can't feed it through into perhaps other analytical methods which you might want to try. The other thing as well is the need for hydrogen. So common to these is the need for a compressed bottle of hydrogen. So this is both a health and safety burden. It's also a burden on consumables. If you're wanting a small bottle of hydrogen for a portable FID, then effectively you're talking a maximum of 8 hours capacity. So every shift you have to get a brand new bottle of hydrogen, attach it to your FID, and start up again. So it's a very powerful, very useful method of detecting VOCs, but it comes with some quite significant difficulties to work around. I'll just quickly go through the other two technologies. Not something which we deal with in Iron Science, not something I'm wholly on top of, but worth talking about because they are growing in the market. One thing is the use of infrared. So what you're dealing with here is absorption of infrared. So you'll pass your gas through a chamber, you'll shine your infrared lamp through the gas onto a detector, and effectively, depending upon the VOC or the chemical, it will absorb particular wavelengths of the infrared lamp. So with your optical filter, as the sample passes through, you'll see some drop in the absorbed spectrum of the infrared. So it's a very useful technique. Can be quite a very cost-effective technique as well. Part of the problem is the need for constant recalibration. We've yet to be able to stabilize this particular technology, but it does monitor all VOCs. So I don't think I mentioned with FID, it goes down. It can measure the methane content in there as well, something which is one drawback of PID. So the FID you can do that with FID. It's also a benefit of the NDIR. Also very reliably picks up the methane as well. So there's also a upcoming technology. At the moment, it's still making its way into the market. It's still being developed, and this is also using infrared, Fourier transform infrared. Fourier transform is basically a very clever kind of mathematical way of separating different wavelengths. So effectively, you're dealing with the same kind of technique as the NDIR. You're looking at infrared absorption. But the clever thing with this is that there is a certain degree of speciation available. So with the other technologies, in some ways, you're just measuring total VOCs. With this technology, there is actually some ability to actually simultaneously speciate the different VOCs. The problem is at the moment is that there's a very high cost. It's much more expensive than the other technologies. It's yet to be really kind of taken on and approved by various people, and it's something which is taking its time. It's coming into the market and waiting to be adopted. But we are seeing this in in smaller units. You can get this in portable versions. So given the different techniques for monitoring we have, there's also a number of performance attributes which we want to look at. There's a particular document which I looked at for this, which if people are interested, email me, I'll provide kind of the documents. But this one, what is called the AIHA Standardized Equipment Specifications Sheet Program for Real-Time Detection Equipment, published in 2013. And it's a fantastic document which lists what kind of attributes are important and how we can consolidate across the industries, how we define what the performance parameters are for our instruments. So one thing you find at the moment is there's a whole number of different specifications over different instruments, and it's very hard with something as broad as VOCs to define exactly how you want your instrument to perform and how you can assure from the technical specifications delivered to you as to what is useful for your application. So it's going through the different attributes which are useful for these. So we have generally your measuring range. So if you're dealing with indoor air quality, you're talking about the ppb, ppm limits here. If you're talking about lower explosive limits, then you're talking about your percentage, your tens of thousands of ppms, or you're talking somewhere in between. So you need to define under what range of concentrations you're looking at here. Perhaps also your minimum detection limits and your resolution. So with the particular technology, how small a concentration can it actually measure? So the different technologies and instruments can range from 1 ppb up to tens or hundreds of ppbs as minimum limits. So it's very useful to choose dependent upon what level you want to get from these. Also resolution and accuracy. So what definition can you get? A 0.1 ppm definition from this, or does it just do large step sizes? And how accurate is it? So with some technologies or monitors, they're used for general monitoring. Other technologies will actually give you a very accurate representation of the VOC concentration in the atmosphere or perhaps the particular process line which you're wanting to monitor. Also sampling rate. So as we've seen, you can have continuous monitors. So if you want something like a handheld monitor where you want a continuous update of the VOCs to ensure that on a continuous basis, real-time feedback of what you're exposed to in the environment? Or do you want something which you can send back to a lab, so on a daily basis you get your VOC feedback? Do you want it monitoring every hour? Do you want a daily sample? Also response times and clear down times. So also with these technologies, you'll find that when exposed to a particular environment, there's what we call a response time and a clear down time. So this is the time it takes for the monitor and its analytical system or its detection method to equilibrate with the sample or the environment which it's in. So you'll see these quite commonly in our technical specifications. Usually we define these as T90 for response time. So this is 90%, the time it takes for your monitor to reach 90% of your response to the ambient gas. So say with PID, our response times are usually 2 or 3 seconds, but you can find with other technologies response times which go into the minutes. Also clear down times. So you also find sometimes with technologies you find, oh great, you stick it in a gas and wow, it reacts really quickly. But it's also very important that once you take your monitoring or your sensor away from that particular environment, that it clears down as well. So you also find out with particular monitors or particular technologies, if they're not designed correctly, that there's a big hang up. A lot of this is down to the design of the monitors and the design of the equipment itself. Your sensors will have a particular clear down time, but you do find with bad instrument design that leads to long clear down time. There's also operating conditions. So the kind of the temperature, the ambient temperature of your environment. So is it going to be cold? Is it going to be hot? Is it going to be humid? These things can adversely affect your monitoring devices, and it's very important to know how the devices are affected by these. Also, how long these devices are going to operate for reliably without operator interference. How much cost will there be for service and calibration? How frequently will we have to service and calibrate them? Also, how much training? How easy are these monitors to use? So there's a lot of different attributes and characteristics to these monitors which need to be taken into account with. And when presented, once you understand what you want to do and the various factors which can affect the monitors and the technology you want, then you're in a much better position to actually provide a useful, reliable, efficient, cost-effective solution, an effective solution to your needs. So taking all that into account, so it's very broad. Hopefully you're keeping up with this. I say there'll be notes afterwards to understand. So broadly, in terms of setting up your monitoring, the first thing you want to do is understand your objectives. So understand why you're monitoring with VOCs, what you're monitoring for. Do you want short-term monitoring, personal monitoring? Are you monitoring process lines here, or are you monitoring ambient environments? Are there particular regulations which you're wanting to uphold? So setting down your objectives. So once you have your objectives, you want to identify the appropriate techniques. So are you going to use grab sampling here? Are you going to use process monitoring? Are you going to have something in line for continuous monitoring? Are you going to have personal monitors? From that, you can decide, do you want somebody within, do you want to base this within house, or do you want a contractor? So there's benefits and deficits here. Contractors bring with them an awful lot of expertise with them. At the same time, you need to ensure that you communicate with them your needs and your desires. And sometimes you'll find there is some financial overhead as well. So it's a balance between how much control you have and how much you're willing for professional people to come in and run this up. So all these together, you have to balance the cost. So what's the expenses here? How much is this monitoring going to cost us? What are we going to get from this? So with all those four things taken into account, you can review this, and with all the different aspects which I've gone through in terms of your compliance, your different methods, your different sampling regimes, you can select your appropriate means of monitoring for these VOCs. Then you implement your program, and then generally with the VOCs, it's a continuous program. So once you put the programs implemented, once you devise your program, you've installed your instruments or you're taking your instruments, you have a circular process of monitoring results and revising the monitoring program. So if there's things which you're missing out on, improving your monitoring program, or if there's particular parts which you find you don't need anymore, you can bring down your monitor program. So it's a couple of case studies. These are things which Iron Science have done out in the real world. So this is some case studies for continuous monitoring and the useful and benefits of continuous monitoring. So the first case study here was in Manchester in England. So what we found was there's a residential area next door to a disused petrol station, and the residents there were complaining of the usual kind of acute health issues associated with VOCs. So they're suffering headaches, there's a smell, there's some nausea going around. So they contacted local authorities, and they came around with their spot test monitors, and when monitoring for this, they didn't find anything. So there was nothing they could do. Well, you can smell this stuff, you're suffering these effects, but there's nothing in terms of our monitoring which correlates with what you're seeing. So what we advised was actually a continuous monitoring. So we installed in the basement of these residential areas continuous VOC monitoring. So here's a lovely tourist photo of sunny Manchester. On the left there, you can see the now disused petrol station, and in the back there is the residential area where people were complaining. So looking at the data we got from this was actually quite shocking. So on the left here, you can see the concentration and ppm of your total VOCs. Your data along the bottom. Hold on, I'll just go back there. And as you can see, when we actually installed a continuous monitor, the results are quite shocking. You're going up to peak of about 100 ppm, down 80 ppm, but regular kind of daily peaks of above 40 ppm of VOCs. So what you can see here is a real evidence that there was substantial exposure to VOCs here. In the top right, so what we've done is average the data over a daily thing, so you can see what happens at midnight, and in the evenings there was a real build-up of VOCs where doors were closed. And in the mornings when the doors were open, you have the ventilation, the VOCs dropping down. So the problem that was happening was the people were coming in doing spot monitoring in the afternoons, where there really was no VOCs at that time for them to see. But with the continuous monitoring, you can actually see that there were particular repeated periods in the day where this was happening. So you can see the importance here of ensuring that your monitoring is covering times when the VOCs will be around. There's a real danger if you don't understand the source of the VOCs and how they're coming about. If you do spot monitoring, chances are you'll miss these kind of episodes. So the second case study we're looking at here was with Hurricane Sandy in America, I believe. So these were underground storage tanks which were disrupted. So this is VOC leaking into the soil and groundwater. So similar kind of exposures to what we saw in the previous one. So what we're looking at here is the use of VOC monitors for remediation. So in the same way we had a continuous VOC monitor installed here. On the purple scale here, so on the right you see your VOC levels in ppm. So at the beginning here up to the say the 29th of November, there's high levels of VOCs. So what was used here was the continual monitor to show how a remediation program could be monitored and validated using this. So a number of techniques were actually used to clear up the contaminated soil and ensure that the basements of these buildings were clean and not exposing the residents or any future residents this not to be exposed to VOCs. So you can see on the 29th there's quite a sharp decrease in the VOC exposure. And also some interesting trending with temperature as well. As you can see, there's some dependence upon VOC exposure and temperature. But still, after this period of time, there's still 10 ppm sitting around. So we went through quite a substantial remediation process. So we removed all the oil from the concrete, installed sub-slab vents, poured concrete into the basement of this. And the final part was the sealed epoxy paint on the bottom. The sealed epoxy paint was painted at the ends. After the concrete was poured, we're still seeing high background of the VOCs. So you can see here around the kind of 15th of December, 16th of December. This is the period of concrete pouring and then the epoxy paint. So you can really see here how throughout this process there comes a point when there's some surety that after this we've sealed off the VOCs, and for a period of days afterwards there's no more exposure, no more outgassing of these VOCs. So with continuous monitoring we're sure that we've solved this problem, remediation has been successful, and we're happy that the job here has been done. Talking about here is benzene. So with benzene there's particular dangerous risks. It's known as a carcinogen. So it's known as known to give leukemia, chromosomal aberrations. It's something which is still very much present within industrial processes, refineries as well. Quickly go through the regulation history of benzene. As we can see in the 1890s, there's various cases of deaths to exposure to benzene. This was in just standard manufacturing processes using solvents, making rubbers, cycle tires, umbrellas, things like that. In the mid-1950s, there's the first indications that benzene is actually going to be regulated. So we start off with a 100 ppm benzene limit, even though back in that time benzene levels of poisoning were between 10 and 25 ppm. So slowly the regulations start to catch up. Soon after that, regulations are brought down to 50 ppm, then they're brought down to 35 ppm. But already the industry wises up. So the American Petrol Institute, through direct recordings of deaths and leukemia through the exposure of benzene, suggests that the only absolutely safe level is 0. But unfortunately, there's this continual balance or fight between regulation and industrial need. So what actually happens is they actually recommend 50 ppm or less, knowing that there is this danger to benzene. They're insistent that we have to retain a higher regulation to ensure that the industry keeps them turning. So what we see here is a continual trend, this pushing down of the benzene regulation as time goes on, and this continual fight from industry. So you see in the mid-1970s direct link of leukemia to benzene. A desire to reduce the exposure to 1 ppm, but yet again there's call from the API to challenge that and retain the 25 ppm limit. So as you go on, there's the continual battles. And it's not until the mid-1980s do we find that the regulation comes in to severely limit the benzene standard down to 1 ppm, and there's real regulation which comes into line with what we know about the health effects of benzene. Unfortunately, the delays which bring these in causes many deaths, and it's these delays in the standardization of regulations which continually causing deaths within industry. So as you can see, it's a general, as we've seen with the PCE, as we've seen with the other CFCs. What we've seen is a history where there's abundant use, and then in the mid-20th century we come in with the regulations and really try and crack down on this stuff. I'll skip through this. Also with domestic exposure, there we go. So also with outdoor air quality, you see in the 1990s there's very high levels of benzene in outdoor air, and it wasn't until the introduction of catalytic converters and reduced benzene vehicles that actually brings down the outdoor air quality as well. So really the 80s and the 90s have seen a crackdown on benzene, and regulations are starting to crack up now. So in terms of industrial exposure, which is where we're heading to with this new instrument which we're developing, we're looking at oil refineries, chemical and petrochemical plants, foundries and catalyst usage, the distribution of benzene and other solvents. So what we've developed here is our own specific benzene monitor. Unfortunately, I have to go through this very quickly. I'm sure it'll be very interesting, and you want to know more afterwards. So what we've done with this benzene monitor is use our PID technology, which we're very knowledgeable about over the years of use, and with it combine a particular selective filtering technology to ensure that the actual reading we're getting, we're feeding the environmental sample into the PID, an actual particular a sample of the benzene separated from the other particular cross-contaminants. So when we're sampling this, we know that the PID is only picking up the benzene. So what we're doing with this is having a sample going through the feed line, and within the center of this there's a carbon filter going through the filter tube into the PID. And then once a minute we're taking a sample from this feed line and feeding it through the filter and the pump, which gives us a 1 minute reading. There's other considerations we've taken into this. So we have internal heating systems to ensure that this is stable and works reliably. So if you briefly go through the technical specification here, so we're working with PID technology to make a benzene-specific monitor. We're working down at a once per minute monitoring, once per minute response time. So what we have here is a truly continuous benzene-specific monitor, which can be wall-mounted within industrial areas and give detection limits down to 0.1 ppm every minute. We've also designed this for hazardous areas, so it's got ATEX and ICX approvals, and we're pending American approvals as well. And just give you a brief study over why we think this is very important technology. So we've actually trialled this against a GC in Singapore. So as you can see, the GC is taking a sample once an hour over many different lines, whereas the Titan is monitoring every minute. So looking at this is real data that we got from our Titan, explicitly superimposed over the GC data. The first thing you can see here is that there's actual episodes here which the GC doesn't pick up at all. The blue being the Titan, the red being the GC. So the first thing is there's just points where the GC is missing it because it doesn't have this short span in selection. So that's one benefit we're seeing here. And other benefit is really quite nice bit of data we see. So we highlight this spike here. You can see the GC gives you this 0.1 ppm spike there, and the Titan goes up to 0.6 ppm or so. But if we zoom in the scale there and actually look what's happening, the data you get from the GC is just this one spot reading for that 1 hour point of a 0.1 ppm. And with this 1 minute reading with the Titan, what you're getting is a much clearer definition of what's happening in real time in that local exposure. This also allows much better definition of both short-term exposure limits to workers in the vicinity, and also a really much more accurate time-weighted average as well for kind of workplace exposures. So if I briefly give you a little overview of the different attributes of the Titan. So one thing we're really dealing with here is something which is selective, sensitive, continuously monitors, and the other benefit here is that it's very cost effective as well. Compared to the GCs, I mean, GCs do benzene specific. With the Titan, we've designed it to be a fraction of the cost of a GC, plus much more user friendly. So in terms of your general your costings for installing this and how it's going to function, it should be what we're looking for is something which is more closer to a plug and play instrumentation, something much closer to what we're usually providing our customers with very simple instrumentation, very easy to use, which gives very straightforward feedback. So hopefully, I'm sorry I had to kind of blast through that last part, but just a review of what I've talking about. I've just given you an overview of what VOCs are, their associated risks, the exposure environments, the technologies, the selection methods of VOCs, and then some idea of benzene, so the importance of benzene monitoring, and hopefully what Titan can bring to the market, and the benefits in terms of protection to human health and our processes. And if you've stayed on over the hour, so I'd just like to say thank you.